This is problem set 2 associated with the Biochemistry Free-for-All book. And I'm Kevin Ahern. I'll be here to take you through the problem set. The first question asks students to order the following molecules from highest oxidation state to lowest oxidation state. And it gives 4 molecules: methane, carbonic acid, formaldehyde, and methane. Well, I start this by thinking about oxidation state, reminding everyone, of course, that oxidation involves the loss of electrons and reduction involves the gain of electrons. If we take several molecules of carbon, or several molecules containing carbon, all of which contain the same numbers of carbon, and those that differ only in their oxygen state, as we refer to it, we can order them in terms of the ones that are the most oxidized and the least oxidized. This is sort of a review of organic chemistry. If we oxidize, for example, methane, CH4, by igniting it in the presence of oxygen, what we do is we generate a lot of heat in the first place, and the products of that reaction are carbon dioxide and water. Carbon dioxide is the highest, most oxidized form of carbon. We see a release of a lot of energy as a result of burning of the methane. This is what heats most of our houses in the United States in the wintertime. And the carbon dioxide can't be oxidized any further. So we can think of carbon dioxide as being at the end of the oxidation state, and methane really as being at the beginning. And we note that methane, of course, contains no oxygen. I've taken and written the 4 different molecules that I asked in the problem here, and also included carbon dioxide on the side. And what I've done is I've actually ordered them from the least oxidized, in the case of methane, all the way up to the most oxidized, which is carbon dioxide. Now, alcohols, of course, are at a lower oxidation state than aldehydes are, so methanol is closer to the reduced state than is formaldehyde. And that oxidation of methanol, you would predict, would generate more heat than the oxidation of formaldehyde, and you would be correct because, again, the farther or the more reduced a compound is, the more energy it will release upon its oxidation. Formaldehyde, of course, is at a more reduced state compared to carbonic acid, as you can see here. And so, again, if we were to oxidize formaldehyde, we would realize more energy from the oxidation of formaldehyde than we would of carbonic acid. Question number 2 asks, based on electronegativity, predict the strength of hydrogen bonds involving hydrogens of sulfhydryl groups compared to hydroxyl groups. So this is a question that really gets you to think about the electronegativity and the role of electronegativity in the uneven distribution of charge. So we can predict then that if we have an atom that has a high electronegativity and it's bonding to a carbon, that there's going to be an unequal sharing of electrons. And of course, that's what we see in the case of oxygen and water. Oxygen has a high electronegativity and hydrogen has a lower electronegativity. So that gap in electronegativity means that oxygen holds electrons more tightly than hydrogen does. The sharing of electrons that occurs between them favors oxygen. Oxygen holds them more closely. And it's for that reason that we see that the oxygen is, in fact, partially negatively charged, as shown in class, and the hydrogen is partially positively charged, also as shown in class. That gives rise to hydrogen bonds, and hydrogen bonds, of course, are stabilizing forces for biomolecules. They're also a stabilizing force to help hold water together as a liquid at room temperature. If we compare the electronegativity of sulfur with that of oxygen, the electronegativity of sulfur is less than that of oxygen. So we would predict then that sulfur would hold electrons less tightly to itself than oxygen does, and we would see less of a gap of partial charge between the sulfur and hydrogen, so that a sulfhydryl would make hydrogen bonds like hydroxide would make a hydrogen bond, but it would be a less strong hydrogen bond as a result of that, and that would be, of course, correct. Question number 3 says, porin is a protein embedded in a membrane. Predict how the orientation of its amino acids will be different from those of a protein found in the aqueous environment of the cytoplasm. Well, the key to answering this question is the fact that the environment of a membrane if we look at it, has polar parts on the outside, long tails sticking inside, as we can see here. And this portion of the membrane where the tails are is very nonpolar. Whereas if we have an aqueous environment out here, that aqueous environment of the cytoplasm is all polar. So a protein that's embedded in a membrane is going to be exposed to nonpolar molecules, unlike a protein that's dissolved in water. So we would predict then that porin, which is found here in this lipid bilayer, is going to have a different arrangement of amino acids than a protein dissolved in water. Now, in the lecture associated with this in the protein structure and amino acid structure parts of the book that I talked about, I noted that if we take a protein and a protein is normally dissolved in water, we have the phenomenon, of course, called folding. And folding occurs for any globular protein. That's true whether we have the protein existing in the cytoplasm and aqueous environment or a protein existing in a membrane such as porin does. That folding of the protein gives the protein its ultimate three-dimensional shape, and that three-dimensional shape is critical for its function. Now, I noted that the folding of the protein in an aqueous environment causes there to be an uneven distribution of amino acids based on their polarity. Proteins that are dissolved in an aqueous environment will tend to have more hydrophilic amino acids located on the outside of the folded protein, and they will tend to have the more hydrophobic amino acids folded into the inside part of the protein, and that's largely due to the chemistry of the hydrophobic amino acids. Where hydrophobic amino acids can avoid water, they do, and they bond with each other, and that's how they end up being more commonly in the inner part of a protein dissolved in water. That's really not any different than taking oil, for example, which is very nonpolar, mixing it with water, and we see that oil doesn't dissolve in water. In fact, it forms little droplets, or if we put enough, we get 2 layers of that. They separate out, and that's because the oil is associating with itself and not with water. So when we see this hydrophobic interactions that cause the hydrophobic amino acids to be inside of a protein, it's really the same thing that's happening with oil and water. Well, now we think about what happens in the case of the membrane protein like porin, and we discover that there's really a different kind of phenomenon that's going on. The parts of porin that are nonpolar, that is the amino acid side chains of porin that wouldn't like water, are perfectly comfortable in the environment of the inner part of the lipid bilayer because that's all nonpolar within there. Those portions of porin that are in that nonpolar part of the lipid bilayer are exposed to it, and they associate with it very well. So it turns out that since a good deal of porin is actually in that inner part of the lipid bilayer, what we see with porin is that it has a sort of a flipped backwards orientation of amino acids. Porin has its nonpolar amino acids more commonly associated with its outer portion, which is where it interacts with those nonpolar tails of the lipid bilayer. And on the inner portion of porin, that's where hydrophilic amino acids are commonly found. Now, what I haven't told you about porin is that porin is involved in acting like a pore. It allows water to pass through it. And so water is actually moving through the inner part of porin. So having those polar amino acids located on the inside allows for the passage of water, and having the nonpolar amino acids preferentially on the outside allows it to exist in the confines of a lipid bilayer. So the next question down says, using the Henderson-Hasselbalch equation, explain why, when a solution is at a pH below the pKa for an acid, that more than 50% of the molecules have the proton on, not off. Now I'm going to move this and pull up a sheet to work on to answer that question for you. First, I'd like to start with thinking about what's happening with the dissociation of a weak acid. A weak acid dissociates like this. And as I noted in class, a weak acid and salt differ only in the whether or not they have a proton. The salt lacking 1 proton compared to the weak acid. Weak acids, of course, don't completely dissociate. The Henderson-Hasselbalch equation relates these things and says that the pH is equal to the pKa of the weak acid plus the log of the salt, which in this case is the A minus, all over the weak acid itself. Now, the question then was asking us, well, why, if the pH is below the pKa, that this ratio is such that there's more of the weak acid than there is of the salt? Well, the best way I can give this problem would be to actually give it numbers, but for the moment I won't do that. I'll just simply say, well, let's bring pKa to the other side, pH minus pKa equals the log of the A minus all over the HA. And since I said now that the pH is below that of the pKa, that means that the pH is less than the pKa. So if I take a smaller number and I subtract a bigger number, I'm going to get a negative number. And that's equal to the log of A minus all over HA. Well, if you remember your basic algebra, you will remember that when the logarithm of a number is negative, it means that the number that's being taken the log of is less than 1. So that means, of course, that the A minus is less than HA. Okay? Now, if I plug in actual numbers here, let's say I pick a pH of 3, where I say 3 is equal to the pKa of a weak acid, and we'll pick acetic acid here, for example, and say 4.76, plus the log of A minus all over HA. If we do that, now we work with the actual numbers, we see minus 1.76 equals the log of A minus all over HA. And that, getting rid of the log term, we see 10 to the minus 1.76 equals A minus all over HA. Well, of course, 10 to a negative power means that we're talking about a fractional number, a number that's less than 1. This number is on the order of between 0.1 and 0.01. Of course, that range of numbers is all less than 1, meaning, of course, again, that A minus must be less than the concentration of HA. And these, of course, all are concentrations, I should note. And that's true for everything on here. Problem number 2 says that using the Henderson-Hasselbalch equation, determine the ratio of acetate ion, salt, to acetic acid present in a 1 molar solution at the following pHs. And then it gives the pKa of acetic acid as 4.76. Well, as you see as I go through this, there's a pattern to how these things play out. But let's take a look at that problem. Well, if we start with, for example, pH 1, we remind ourselves, first of all, that ionization of acetic acid proceeds as H plus plus AC minus. I always like to have students remind themselves of this. Remember that the pKa value for this ionization is 4.76. And the question asks at pH 1, the ratio of acetate ion to acetic acid. Well, remember Henderson-Hasselbalch equation says that the pH equals the pKa plus the log of the concentration of the salt, which in this case is AC minus, divided by the concentration of the acid, which is HAC. Well, plugging in our values at pH 1, we see that the pKa 4.76 plus the log concentration of AC minus over the concentration of HAC. Taking the 4.76 to the left side, we get minus 3.76 equals the log of salt, which I'm just going to write as S, divided by acid, which is right here. 10 to the minus 3.76 equals the ratio of S over A. So I've actually found the ratio of the salt to acid here. Now, in my class, I tell my students that I only want them to get to the point where they would punch it into a calculator. I don't care that they punch it into a calculator, and so I'm not going to punch it into a calculator here. Suffice it to say, you should have some idea about what that number means. 10 to a negative power, of course, is a number less than 1. 10 to a minus 3.76 is a number that's fairly small, meaning, of course, that there's a lot more acid present in that solution than there is salt. Well, I can similarly do the problem at pH 2 and see that 2 equals 4.76 plus the log of AC minus all over HAC as before. Now minus 2.76 equals the log of the salt all over the acid. And 10 to the minus 2.76 equals the concentration of salt over acid. And again, I have solved the problem. Notice here that 10 to the minus 2.76 is not quite as small of a number as 10 to the minus 3.76. So it means that there's now more salt to acid ratio. There's more salt. There's a little bit more ionization that has happened at a higher pH. And that's not surprising. The higher the pH, the more ionization or the more loss of protons we will see by the acetic acid. Well, if I extend that to the other problems, I'm not going to go through and do it for pH 3 and 5 and so forth because I think you can start to see the pattern. But let's say pH 7. At pH 7, I can see that the ratio of salt to acid now has changed in the other direction. It's 4.76 plus the log of salt over acid. The salt, of course, being the acetate, the acid being the HAC. 2.24 equals the log of the salt over the acid. So that 10 to the 2.24 is equal to the ratio of salt over acid. So again, I've solved the problem that I was asked to solve. In this case, I see that the exponent on the 10 is a positive number, meaning that the ratio of salt to acid is greater than 1, meaning, of course, that I must have more salt than I have acid. And that's not surprising. When we get to pKa values higher than the salt, we get to pH values higher than the pKa, we will have more salt present in the solution than we will have acid. And the higher the pH goes, the higher that ratio of salt to acid is going to be. The third problem says that at physiological pH, what will be the predominant form of phosphate present in cells? H3PO4, H2PO4 minus, HPO4 minus minus, or PO4 minus minus minus. And I give the relevant pKa values here as 2.12 for the first ionization, 7.21 for the second ionization, and 12.87 for the third ionization. And then I ask you to justify your answer using the Henderson-Hasselbalch equation. Well, let's start by thinking of that ionization first. So phosphoric acid has 3 different protons that it can lose. It starts with H3PO4. That's known as phosphoric acid. And it can ionize to form H2PO4 minus with the loss of a proton. H2PO4 minus can lose a proton also and become HPO4 minus minus with loss of a proton. And HPO4 minus minus can also lose a proton and produce PO4 minus 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 with loss of a proton. Now, you'll note that I started with 4 different forms of this phosphate. H3PO4, H2PO4 minus, HPO4 minus minus, and PO4 minus minus minus. You'll notice that there's only 3 pKa values, and that's because pKa's are always associated with ionization. So with ionization, we have 2 possible forms, the form that has the proton and the form that doesn't have the proton. So the pKa values that I gave you were 2.12, corresponding to the ionization or loss of the first proton, and the lowest pKa value will always be the loss of the first proton. The second pKa value I gave you was 7.21, and the third pKa value I gave you was 12.87. Now, some of you may be working problems that have slightly different pKa values. I think I had a version of the problems that were out that had some slightly different pKa values, and those slightly different pKa values do, in fact, affect the way the problem works. So if you, problem is solved. If you see differences in your answer and my answer, check to see the pKa values that you used for the problem that you solved. Well, the question asks is, what's the most predominant species, the most common species that we find in this solution at pH of 7? Well, at pH of 7, that's approximately physiological pH, we can actually answer that question fairly readily. So what I'd like to do is go through a process of elimination and determine what is the most likely species that's present. If we start, for example, and say, well, is it H3, if we compare H3PO4 and H2PO4 minus, we can say which one of those is most predominant at pH 7. And that's a fairly easy question to answer. When we answer that question, we can eliminate one of those. So let's do that. We start with the Henderson-Hasselbalch equation that says pH equals pKa plus the log of, in this case, H2PO4 minus, PO4 minus, divided by concentration of H3PO4, salt over acid. Plugging our numbers in, we see that the pH of 7 equals the pKa of 2.12 plus the log, and I'm going to abbreviate here as the salt over the acid. Well, when we do that, we see that taking the 2.12 to that side, we get 4.88 equals the log of the salt over the acid. And that means that 10 to the 4.88 is equal to S over A. Well, 4.88, of course, is a positive number, meaning that this number is greater than 1, meaning, of course, that there has to be more salt than there is acid. Well, the salt form here is H2PO4 minus. That means that the acid form can't be the most abundant form that's present inside of cells. So now we have eliminated this one. Next, we can go to the other side and say, well, between HPO4 minus minus and PO4 minus minus minus, which is the most abundant at pH 7? Well, if we look at pH 7, and we say that pH 7 is equal to 12.87 plus the log of the salt form, which is PO4 minus minus minus. Remember that the salt form is always the form that has the fewest number of protons between a given two species. Now, we'll see that some things can be a salt or an acid depending upon which ionization that we're talking about. In this case, HPO4 minus minus is the acid because it has one more proton than the phosphate PO4 minus 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 does. Well, doing all this, we see that minus 5.87 equals the log of the salt, which is the PO4 minus minus minus, divided by the acid. And, of course, these are concentrations again. And 10 to the minus 5.87 equals S over A. Well, 10 to a negative exponent means that the number is less than 1. If the number is less than 1, it means that there has to be more acid than there is salt. Looking back at our equation, comparing the HPO4 minus minus and the PO4 minus minus minus, the HPO4 minus minus is the acid. It's the form that's the predominant form, and we have now eliminated PO4 minus 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 from consideration. So the most abundant molecule that's present in the cell, in this reaction, has to be either HPO4 minus or HPO4 minus minus. Now, in the first reaction, H2PO4 minus was the salt. We see in this ionization it's the acid because it has one more proton than HPO4 minus minus. Well, let's plug these numbers in. We see at pH 7, we have a pKa for this ionization of 7.21 plus the log of the salt form, which is HPO4 minus minus, divided by the concentration of the acid, which is H2PO4 minus. Bringing our terms over, we see that minus 0.21 equals the log of the salt form over the acid. 10 to the minus 0.21 equals S over A. Well, remember again that 10 to any negative power means that this ratio must be less than 1, meaning, of course, that we have to have more acid than we do salt. So in this case, we have more acid than salt. The acid is H2PO4 minus, the most predominant form in the solution, therefore must be the molecule that you see here. Okay, so that solves that problem. The next problem asks that says that formic acid has a pKa value of 3.75 and acetic acid has a pKa of 4.76. And then it asks, why do we consider formic acid to be a stronger acid than acetic acid? And it says your answer should have a mathematical basis. Now, I've talked to a lot of students about this problem, and they say, well, formic acid must be a stronger acid because it has a lower pKa value, and that's what I talked about in class. And the answer to that is that's consistent. However, it doesn't answer the question, meaning that why is it that it's a stronger acid? Well, before I say go to work this problem, I want to think about what does it mean to say something is a stronger acid. I've talked in class about how HCl, for example, completely ionizes when we put it in water. And when I talked about that, I noted that that was a strong acid. So something that completely ionizes in water is a strong acid. Something that does not completely ionize is a weak acid. Well, a stronger weak acid would ionize more than a weaker weak acid. And that's really the bottom line of what we work with in this problem. So let me step you through this. Let's consider, for example, formic acid, which I'm going to label as HFA, ionizing to F, let's just call it F, HF minus plus H plus. And let's also think of acetic acid as HAC going to as AC minus plus H plus. The pKa value for the top one is 3.75. The pKa for the bottom one is 4.76. Well, how do we answer that problem? What I like to do is to do it by example. Let's imagine that we had a pH. We can pick any pH value that we want because the answer that we're going to have here is going to be true at any pH value that we happen to pick. So let's pick a pH value that is very easy to work with, and let's say how ionized is each of these species at 3.75, okay? So the one that's the most ionized, that is the one that has lost the most protons, would be the one that is the strongest acid. Well, if we look in the case of formic acid, we can say that when the pH is equal to 3.75, it's equal to the pKa value, which is 3.75, plus the log of F minus all over HF. Okay? Well, when I take this to this side, I see that 0 equals F equals the log of F minus all over HF. And 10 to the 0 equals 1. And that therefore equals the concentration of F minus all over the concentration of HF. So what that tells us is at this particular pH that I've picked, the amount of the salt, which is the F minus, is equal to the amount of the acid, HF. Well, at the same pH, how ionized is acetic acid? Well, it's very simple to answer that question. We simply say that at pH 3.75, the pKa of acetic acid is 4.76 plus the log, the concentration of AC minus, all over the concentration of HAC. I bring this to this side, I get minus 1.01 equals the log of the concentration of AC minus all over the concentration of HAC. Raising 10 to the power of minus 1.01, that's equal then to the concentration of AC minus all over the concentration of HAC. Well, we remember that 10 to a negative power means that that number is less than 1. That number being less than 1, then corresponds to the fact that HAC is more abundant than AC minus. That means, therefore, that less HAC has ionized at pH 3.75 than formic acid. Formic acid had an equal amount of formic acid salt and formic acid acid present. So at the same pH, formic acid has ionized more, and for that reason we can say that formic acid is a stronger acid. Okay, let's turn our attention now to problem number 5. In problem number 5, it says that you have a liter of a buffer solution of acetic acid with a concentration of 0.8 molar. The pKa of acetic acid, of course, is 4.76. And it says at pH 4.3, how many moles of acetic acid and how many moles of acetate do you have? Well, this problem is a little bit more involved, but it's not a difficult one. It requires, first of all, that we remember something I talked about in class. And that is, I said that whenever you hear the term buffer, you should always think of two things. You think of salt and acid, and that the amount of a buffer is equal to the amount of salt plus the amount of acid. So I say buffer equals salt plus acid. And I note here that I'm talking about moles of salt, and I'm talking about moles of acid, and I'm talking about moles of buffer. And the reason I'm talking about moles is I can add and subtract moles. I cannot add and subtract concentrations. Okay. Well, this particular solution is 1 liter in volume, and it has a concentration of 0.8 moles per liter, which is the molar concentration. If I multiply the volume times the concentration, I get the number of moles, which is equal to 0.8 moles. My writing is not very good. Of buffer. And notice I'm labeling everything here. It's very important when you're going through a problem to label the quantities that you come up with, because A, it helps to keep you remembering what they were, and you don't have to keep track of them in other ways because they're written down on your sheet. But more importantly, if you're taking an exam and a person is trying to understand your logic, if they can understand your logic better, you're much more likely to get partial credit than if they just simply see a bunch of numbers on the piece of paper without any explanation of what they are. Hopefully your handwriting is better than mine is. Okay, so we have 0.8 moles of buffer. We remember that moles of buffer is equal to the moles of salt plus the moles of acid. And that will become important for us later as we work the problem. Well, this problem said that we had a pH of 4.3, and it wanted to know what the number of moles of salt, number of moles of acid was in that buffer. Well, we start that problem by working with the Henderson-Hasselbalch equation. It says that the pH, which is 4.3, is equal to the pKa value of the acetate system, which is 4.76, plus the log of the concentration of salt all over the concentration of acid. Now, when we do that, I want to point out that these two concentrations are actually equal, meaning that they're in, I shouldn't say that they're equal, but that they're both in the same volume. Well, since the two volumes are, in fact, equal, that means that we can really work with these comparing moles instead of concentration. So if I compare the ratio of moles is going to be the same as the ratio of concentration since they are in the same volume. So I can write that equation as 4.3 equals 4.76 plus the log, in this case, of the number of moles of salt divided by the number of moles of acid, again, because they're in the same volume. Well, when I do that calculation, I see that minus 0.46 is equal to the log of the number of moles of salt divided by the number of moles of acid. 10 to the minus 0.46, therefore, is equal to the ratio of the number of moles of salt to the number of moles of acid. Well, remember that the problem asks not for the ratio, but it asks for the number of moles of each. Well, this is two unknowns in one equation, and of course, we can't solve two unknowns in one equation. But we remember that earlier we had an equation that also involved moles of salt and acid, and that equation was shown up here. So what I can do is then rearrange the equation above to solve either for salt or for acid. I could say that salt equals 0.8 minus the number of moles of acid, or I could say that acid equals 0.8 minus the number of moles of salt. And it doesn't really matter which one I choose. I'm going to say here that the number of moles of salt is equal to 0.8 minus the number of moles of acid. Well, in that case, I can now substitute into this equation and say 10 to the minus 0.46 is equal to 0.8 minus the moles of acid, I'll just write as an A, divided by the number of moles of acid. Well, I don't know what that 10 to the minus 4.76 is because I'm not carrying my handy-dandy calculator with me. So I give the letter Z to whatever that value is. So Z is simply the number that corresponds to 10 to the minus 0.46. And students in my class won't be using a calculator, so it would be perfectly appropriate for you to do something as I have done here. Z then is equal to this. So we say Z is equal to 0.8 minus A divided by A. Well, if I multiply both sides by A, I get ZA equals 0.8 minus A. And I can then bring A over, saying that ZA plus A equals 0.8, and that A times the quantity Z plus 1 equals 0.8. And now dividing both sides by 0.1, I get A equals 0.8 divided by Z plus 1. I have now found the number of moles of acid. Well, how many moles of salt do I have? The number of moles of salt that I have is equal to 0.8 minus the number of moles of acid. So the number of moles of salt I have is equal to 0.8 minus 0.8 divided by Z plus 1. And that's equal to the number of moles of salt. Okay, so I have solved the problem and found the number of moles of acid and salt, depending upon whatever that 10 to the minus 0.46 corresponds to. Okay. The next problem says that a new molecule is discovered called blemium. It contains ionizable groups with the following pKa's. Carboxyl number 1 has a pKa value of 2.2. Carboxyl number 2 has a pKa value of 4.4. Amine number 1 has a pKa value of 5. Amine number 2 has a pKa value of 8.5. And amine number 3 has a pKa value of 9.5. And I've been asked then to predict the charge of blemium at the following pHs, a pH of 1, a pH of 7, and a pH of 11. Well, I haven't given you a structure, so let's just draw out a theoretical structure of blemium just to kind of help us to keep track of what it looks like. So let's imagine blemium looks like this, and you can pick any structure that you wanted for this. So let's say there's carboxyl group number 1, and I'm going to draw these first with all of the protons on. There's carboxyl group number 2, and here is amine number 1. And since I'm putting all the protons on, I've got that, NH3+, and last, and these of course all have hydrogens around them, like so, and an NH3+. Okay, so it says predict the charge on blemium at the following pHs. So we'll start with pH 1. Now, to estimate the charge of something, as I noted in my lecture, you can make the reasonable assumption that if the pH is 1 or more values below the pKa of a given group, then the proton for that group is on. Now, when students look at a problem like this, I find that they're frequently confused because they say, well, which one are we talking about? And first of all, we have to compare each individual pKa value. So we're going to say this was number 1, number 2, number 1, 2, 3. Okay? And remember that all of these groups are present in the molecule, and the molecule is present in the solution that all has a pH of 1. So if I start, for example, by saying, well, at pH 1, all I have to do is ask if each of those protons is on or off of that molecule. Well, at pH 1, 1 is more than 1 unit below 2.2, meaning that the proton on number 1, which is this guy right here, is on, meaning that the way I've written it is correct. I have a COOH, and a COOH, of course, has a charge of 0. Carbon number 2, or carboxyl number 2, is right here, and it has a pKa value of 4.4. 1.1, of course, is more than 1 unit below that. So this proton is also on. This charge is 0. Amine number 1 has a pKa value of 5, and 1, of course, is more than 1 unit below 5. So it has a proton on, as I have drawn, and it has a plus charge, as I have drawn. Well, you can see the same is true for the 8.5 and also for the 9.5, because 1 is more than 1 pH unit below those. In this case, 1 the pH of 1 is more than 1 unit below the pKa values of all of those groups. So all of those groups have a proton on them. And when we look at that at pH 1, we can see that the charge is equal to a +3. Well, if we do the same exercise at a pH of 7, we start seeing some different things happening. First of all, pH 7 is more than 1 unit above the pKa of the carboxyl group number 1, meaning, of course, that that proton is going to be off. When that proton is off, we end up with a minus charge. Second, we see that the pH of 7 is more than 1 unit above the carboxyl group. So we see that that proton is also off, meaning that we have a charge of minus as shown here. With the amine number 1, the pH is more than 1 unit above its pKa value, so its proton is off, meaning that we've lost a proton. And when we lose a proton off of an amine, we get a charge of 0. For the amine number 2 and number 3, we see that the pH is more than 1 unit below each of their pKa values, so that each of these has a proton on. And the overall charge of the molecule, of course, is the sum of these charges. So we have a minus, a 0, a plus, and a plus. And at pH 7, we see the charge is approximately 0. Remember that when we do PI, we have to calculate PI precisely. An estimate of a charge is valuable for estimation purposes, but 7 is not necessarily the PI value of this molecule. If we now examine this molecule at a pH of 11, we can see that the charge changes again. So let's start at the top with the carboxyl number 1. 11 is more than 1 pH unit above the pKa value, so that proton is off. So we have a COO minus. Carboxyl number 2, pH is more than 1 unit above the pKa value. We see that the proton is off, and we have a minus charge. pKa number 3, the proton is off. We remain a 0 charge. pKa number 4, pH is more than 1 unit above, and so we also have a 0 charge. And finally, the amine number 3, the pH is more than 1 unit above the pKa. We lose the proton, and we have this. Now, when we add up all the charges on this molecule at pH 11, we see minus, minus, 0, 0, and 0, and that corresponds to a charge of minus 2. So as we raise the pH for an amino acid or for a polypeptide, we will see that the charge increasingly becomes negative. Well, the last problem that I have on here is one of the more difficult problems that students encounter, and so I want to work through that with you. Before I work through that, I want to set it up. I want to talk about how this really is 3 problems in 1. 3 problems in 1 are each themselves not impossible to do, and each not impossible to think about. I want to look at this problem and think about what's happening. First, I have a solution that is an acetate buffer at pH 4.5. And it's 1 molar. And of course, we remember for an acetate buffer that the pKa value is 4.76. Well, earlier in this problem set, we worked problem number 5, where we had a pH of 4.3 and we had a pKa value of 4.76, and we knew the concentration of the buffer, and we were able to determine the relative amounts of salt and acid. In this problem, we have the first solution, 1 liter of a 1 molar acetate buffer at pH 4.5. We can use the same strategy that we used above for finding the amount of salt and acid in that solution. And we mix the first solution with a second solution that has 600 milliliters of a 0.5 acetate buffer at pH 4.8. So we could find, for example, in the second solution, the number of moles of salt and the number of moles of acid. So at that point, I could say, well, when I've mixed these 2 solutions together, how much salt and how much acid do I have? Well, the amount of salt that I have present would be equal to the amount of salt in the first mixture plus the number of moles of salt in the second, and the total number of moles of acid I would have would be the number of moles of acid in the first plus the number of moles of acid in the second. Now, in order to do this, I need to be, of course, working in moles because I can add moles, I can't add concentrations. The third thing that happens to this then is that I add a liter of 0.1 molar HCl. Well, HCl is a source of protons. And as we add protons, we see that buffers change. addition of protons causes salt to be converted into weak acid. And that'll be the last part of the problem in order for us to determine the pH. But I'm getting a little ahead of myself. Let's start with the very first part of the problem. In the first part of the problem, I have 1 liter of a 1 molar solution of acetate buffer. So I have 1 liter times 1 mole per, it's like mule, doesn't it? 1 mole per liter. Liters cancel, and I've got 1 mole, oh, there we go, there you can see it, of buffer. And that's equal to salt plus acid. Again, in this case, I'm working with moles. I can then say that the number of moles, for example, of salt is equal to 1 minus the number of moles of acid, as I did before. And I can go into the Henderson-Hasselbalch equation, pH equals pKa plus the log of the concentration of salt over acid. And that's also, in this case, equal to pKa plus the log of the number of moles of salt over acid. So I haven't mixed anything yet, so everything in that first solution is all in 1 liter, and so the number of moles and acid are proportional to the concentration. So I can work with moles just fine at this point. Well, plugging in numbers, I get the pH that I have in the first solution is 4.5 equals the pKa of the acetic acid system, which is 4.76, plus the log of S over A minus 0.26 equals the log of S over A, and 10 to the minus 0.26 equals S over A. Well, again, let's call this number Z, whatever that turns out to be. So we say that Z equals S, and we said S was 1 minus A divided by A. And so now we say ZA equals 1 minus A. ZA plus A equals 1. And A times Z plus 1 equals 1. A is equal to 1 over Z plus 1. Okay? So when I have done that, I have found the amount of A. That's the number of moles of A. The number of moles of Z then will be equal to 1 minus that. So, I'm sorry, the number of moles of salt is equal to 1 minus that. And the number of moles of salt is equal to 1 minus 1 over Z plus 1. So, now, I'm going to label this. I'm going to say this is A1, meaning the number of moles of salt in solution number 1. And this is S1, meaning the number of moles of salt in solution number 1. Well, I can do the same thing for solution number 2. In solution number 2, I have a 0.5 moles per liter solution, and I have 600 milliliters, which is equal to 0.6 liters. So I now see that liters cancel liters, and I'm left with 0.3 moles of buffer in solution number 2. I'm going to put a little 2 down here to designate that. So I therefore say that salt in number 2 plus acid in number 2 is equal to buffer number 2. Okay? Well, going through the same exercise that I did before, I say what's the pH of the solution? The pH of the solution is 4.8 is equal to the pKa, which is 4.76, plus the log concentration of the salt, concentration of the acid. But again, since we're still only talking about solution 2 at that point, we haven't mixed it, we can say then that this is equal to 4.76 plus the log of the number of moles of salt divided by the number of moles of acid. So And again, because solution 2, salt and acid, are present in the same volume. So everything works out with that. Okay, well, if we solve that equation, we can see that 0.04 is equal to the log of moles of salt number 2 divided by moles of salt number, divided by moles of acid number 2. 10 to the 0.04 is equal to S2 all over A2. And I have the same thing I had before. So S2 plus A2 equals 0.3, as I have from above. So that S2 equals A2, equals 0.3 minus A2. So if I plug that into my equation here, I'm going to call this number right here M, which is 10 to the 0.04 equals 0.3 minus A2 all over A2. So now I say that M times A2 equals 0.3 minus A2. MA2 equals the, MA2 plus A2 equals 0.3. A2 times M plus 1 equals 0.3, so that A2 equals 0.3 divided by M plus 1. So I've now found the number of moles of acid in the second buffer solution. The number of moles of salt, therefore, will be equal to 0.3 minus this quantity, 0.3 all over M plus 1. And I now have found the amount of A2, and I have found the amount of S2. Well, that's useful to me. I've done the first two parts of the problem. The third part of the problem is I add HCl to this solution. So I want to start and think, well, let's keep track of everything that we've got here first. First, we have a certain number of moles of salt. The amount of moles of salt we have is equal to the salt in solution number 1 plus the amount of salt in solution number 2. Since they're moles, we can add them. Equals total salt before HCl. The total number of moles of acid before HCl is A1 plus A2 is equal to the total acid, and total moles again of acid, before the HCl. Well, adding HCl, I always want to remind students to write this equation down. HAC ionization goes to AC minus plus H plus. If I add protons, according to Le Chatelier's principle, I will drive this reaction to the left, meaning that for every proton that I add, I will have one of those gobbled up by acetate, meaning I will lose one acetate, and I will gain one HAC. I'll repeat that. For every proton that I add to the system, I will lose one AC minus, and I will gain one HAC. Now that turns out to be important. How many moles, the question then is how many moles of protons do I add? Well, the number of moles of protons that I add is 1 liter of HCl times 0.1 moles per liter. Again, liters are going to cancel liters. And I am adding 0.1 moles of protons. And I can write those as protons because when I put HCl in solution, they all dissolve and become H pluses. The Cl minuses don't affect anything, so we don't even track them after this point. So we've added 0.1 moles of protons. Well, I just told you that if I add 0.1 moles of protons, I'm going to lose 0.1 moles of salt, and I'm going to gain 0.1 moles of acid. So if I now look at my original, or my starting materials, that is the amount of salt 1 and salt 2, and the amount of acid 1 and acid 2, when I add 0.1 moles of protons, I'm going to have 0.1 moles more of acid, for the reason I just stated, and I'm going to have 0.1 moles less of salt. So if I say S1 plus S2 minus 0.1, that will be salt after HCl. And I can say that acid plus acid plus 0.1 will be equal to the number of moles of acid after HCl. The question asks me, what's the pH? Well, pH, I will remind you from Henderson-Hasselbalch equation, is equal to the pKa value of the system plus the log salt over acid. Now, you can convert those quantities there to concentration if you want, but since everything at this point is in the same volume of solution, it really doesn't matter. We can say that the pH of the solution is equal to 4.76 plus the log of the total number of moles of salt, which is S1 plus S2 minus 0.1, divided by the total number of moles of acid. Acid 1 plus acid 2 plus 0.1. If you wrote this answer on my exam, you would have just gotten 100%. Notice I didn't use a calculator. I didn't do anything except show what I would have done to punch all this into a calculator. So this complicated problem is really three problems. A problem first where we find the acid and salt in the first solution, second problem where we find the acid and salt in the second solution, and a third problem where we adjust the amounts of acid and salt by adding an